So good afternoon. I'm Tomas Larsson, and I'm going to talk a bit about some work that we have been doing on chemical and structural methods for characterization of isolated cellulose. And what I will do is that I will present some methods that we have found useful for characterizing isolated cellulose, and I will illustrate by some examples. And actually, some of these methods are what I would call standard methods, but some are also methods that we have been developing over the years ourselves because of basically a lack of good functioning methods. I think my presentation will take about 30 minutes. With that, I will move on. Well, if I should give some kind of background, this goes back some close to 10 years, I think, when there was an idea about making adapted pulps. And with that, we mean basically pulps for other purposes than paper making. And the aim was to achieve this by altering processing conditions using existing equipment. And then adapted pulp, it's of course a rather broad concept, but it can be pulps that can be easily converted to MFC or CNF, pulps with high chemical reactivity, pulps that can be rapidly convertible to sugars by enzymes, pulp with high water binding capacity, and pulps that could be easily dissolved in some selected dissolution system and so on. And it can be more, of course, but in traditional terms, you could actually say that what we would like to do is actually to produce a rather poor paper making pulp. And there is, of course, a tremendous amount of knowledge about how to make a high quality paper making pulp. That's the whole industry knowledge base, so to speak. But the problem then is that when you start to alter processing conditions beyond those typically used commercially, we don't really know what to expect. So the first attempt here we did was, or which I'm going to talk about, is basically a trial and error approach. And the trial and error approach is that, well, you decide on a target, what kind of properties you would like, and then you start to change processing conditions in different processing steps, and you sample and analyze. So, and you try to judge whether you are sort of by the process changing processing conditions, you are moving towards the goal or away from it. But in sort of retrospect after this, there is something that come to my mind that sort of came up to the surface as a result of this, and that's the key, what I would call the key problem, and that is when we move beyond traditional processing conditions, traditional in some sense, we actually lack a systematic understanding of the interplay between the chemistry we use during the processing and the resulting fiber wall nanostructure. And I think this is an important sort of generic question that stuck with me from the work that we did. And also, it was, of course, the first attempt we did was, of course, it was time consuming and resource consuming. And since what we did was to effectively just throw all the analytical techniques we had available on the material, and due to the multiplicity that you have to sample at several different points in the process for several different variations, it's also maybe good to keep in mind that these kinds of projects have a tendency to consume most of the project budget just as characterization work. But in a simple terms, what we want to do is that, well, when we do processing, we, for example, for the purpose of a cellulose-rich fiber, we want to remove components. And typically, you end up removing about 50% of the material, and you go from a rather dense structure into a system that is more like a open network. I mean, the blue here, the blue squares are, of course, indicating water-filled pores or water-filled cavities. But half of the material is essentially removed. So we are looking at the length scale about, say, below 100 nanometer. A more maybe realistic view of this is this. These are two very nice pictures from Jeff Daniel. And I think they are good in that sense that they both represent the fact that we have a hierarchical structure in this material. And the picture to the left over here is essentially a cross section of a fiber where the lignin has been etched away. So you can clearly see this sort of lamellar structure and so on. And the picture to the right is at the larger magnification. You can see these strand-like structures, probably of polysaccharides here. And I think that this picture is most likely from a primary wall, but it really doesn't matter. I mean, in a secondary wall, you would have a bit higher organization. But the concept here is that we have basically a network kind of structure with cavities in it. So size scales, and we are rather focused on size scale, say below 100 nanometer. And the reason for that is simple, and that's because most of the fiber wall surface area, or the majority of the surface area, and the majority of the pore volume in a fiber wall are found below 100 nanometer. We have pores in the region of 10, 20, 30, 40 nanometers, and particle sizes in that region as well. So that's why we judge this sort of size scale to be, for our purposes at least, the most important one. And then there is another thing that's worthwhile pointing out as well, and that is we are what we are now doing in a simple terms is that we are trying to do chemistry in a non-heterogeneous system, and then accessibility becomes a really important concept in several ways. I would say it's whether you can transport things into a fiber wall, where things can react, which part of the solids is actually accessible to reagents or chemicals you add, and also if you need to transport things out of the fiber wall. Accessibility is of course connected to kinetics as well, but I mean, as a generic term, I would say that accessibility is really a central concept to understand what goes on in these systems. So what did we do then that is sort of beyond what's normally done? Well, for the pulps, or for trying to find processing conditions for adapted pulp, we took what we call an extended analysis package for chemistry and structure, and it consists mainly of 4 things. And first of all, it's sugar analysis by acid hydrolysis, where you look at the chemical composition in terms of monosugars and lignin. You look at molecular mass distribution. I mean, traditionally you look at viscosity of pulp, but we decided to go for molecular mass distribution as a more detailed or better description. We have the fiber saturation point measurements. I mean, sugar analysis and molecular mass distribution, they are essentially something telling us about the chemistry in the material. And the fiber saturation point, well, what in a sort of lignin depleted fiber wall, it tells us what's not there, basically. It tells us about the pores and pore structure. And then we use the solid state NMR for taking measure of what's there. I mean, the solid particles and so on. And since this is a bit old, we did not at that time have access to X-ray scattering. So for that reason, it has not been included in this work. But first things first. And sugar analysis is definitely not the most sort of advanced or sexy method, to say the least. But I would say that from my point of view, this is really one of the most important methods that we have. We break down the material by a strong sulfuric acid, and we analyze by ion chromatography. And we can also get a gravimetric determination of the insoluble lignin and so on. And of course, as all analytical method, it's not complications free. It's full of complication. And one is that, well, when we degrade cellulose with sulfuric acid, we also eventually started to degrade released monosugars. So it has no closure. I mean, it doesn't have a mass balance. But in my opinion, this is the least bad method, and it's definitely better than nothing. So I think this is a key thing, that it's really important for this material that we have an understanding for the chemical composition to start with. And you could put it like this, that all the other methods are basically dependent on this one. So this is the foundation of the work we would do when we want to characterize the materials. It's a very important method, and it gives you results something like this. you can get for lignin-containing samples both the carbohydrate composition in terms of monosugars, and you have the different forms of insoluble and soluble lignin up here. And typically this is just reported as milligram per gram. But for samples that become more rich with respect to polysaccharides, the relative composition, the table below here, is the one that I use the most. And I think it's very telling and it's very useful. And it gives you a very good sort of understanding for the starting material or the material that you use. And it's might seem simple, but it's actually built on 3 different standard methods, and it's actually not as simple as it seems, but it's very important. And I think this is one of the most important methods we have, as I said. Well, molecular mass distribution, it's equally complicated and associated with other forms of complication, but the target we used it for was samples that are polysaccharide rich, and you can do limiting viscosity. And at that time when we were trying to set this up, I had a colleague of mine at RISE, Fredrik Aldeus, that went through the literature for the different ways that you can recalculate limiting viscosity into degrees of polymerization. And he came up with 6 different ones, and according to his judgment, they were all equally bad. So for that reason, we settled for doing a full molecular mass distribution determination rather than using limiting viscosity. And here we have a variety of methods where you can dissolve the cellulose by different methods. You have nitric acid, lithium chloride, dimethylacetamide, and 3-carbonylation, etc. We choose eventually to use the method based on 3-carbonylation and detection by or separation by size exclusion chromatography, SEC. I don't remember really why. I think it was because of the dissolution time. I think this is one that doesn't take too long. But what it showed us was that, of course, comparing results between methods that use different ways of dissolving the cellulose is not very fruitful. But as long as you stick with one method, relative comparison between results can be quite useful. So when we use this 3-carbonylation method and for a series of samples, we can track at least in a qualitative way which way things goes and so on. So for that purpose, I think it was found quite useful. The fiber saturation point method, that is looking for structural features, what's not there, the pore size. And it's a solute exclusion method. And you could, if you're familiar with water retention value, I would say that the FSP method is sort of the smart or the intelligent cousin of water retention value. It gives more reliable results, and particularly so, it gives results that are in absolute terms more reliable. And the great advantage of this method, I would say, is that you determine essentially the mass of liquid trapped per mass of solid. And you can do that in the water swollen state. The whole measurement is, of course, performed in the water swollen state. So that's quite useful. And the method works essentially by this, that you have a sample and you have a very large polymer. We use dextran. And historically, I would say, when you say FSP, historically, it actually means a method that was originally designed for determining pore size distributions in fibers. But determining pore size distribution, then you have to deploy a whole set of dextrans with different molecular mass. Some of them will penetrate into the fiber wall and some won't, and so on. And this has been criticized a lot because there are complications with that, with the penetration of swollen molecule into a pore system and so on. But we don't use it as such. We only use the extreme limit of the FSP method, where we have a very large dextran molecule. It's a commercial dextran that's 2 megadalton that has hydrodynamic radius of about, hydrodynamic diameter of about 100 nanometer. And we only use it in a limit where none of the material, none of the polymer can enter into the fiber wall pore system. And that means that we are free of at least some of the complications with the method. But what it gives us are essentially two things. It gives us a measure of the fiber wall, the liquid trapped in the fiber wall, and also it also establishes a operational definition. The deck strand we use is basically the operational definition of what we mean with the fiber wall pore. So basically everything below 100 nanometer are considered to be a fiber wall pore, if you wish, or about 100 nanometers. The NMR, NMR method for looking at the solids of the fiber wall is this cross-polarization magic angle spinning hydrogen decoupled carbon-13 nuclear magnetic resonance spectroscopy. It's actually a technique that is good at taking measures of the supramolecular structure in semi-crystalline organic solids. And it's very suitable for cellulose and cellulose-rich pulp with a low lignin content. You can, of course, use it for lignin-rich samples. You can look at solid-state NMR on lignin, but we don't use it for that quite as much. And one thing that is good, I think, to keep in mind with respect to this method is that, well, you get signals, and signal positions, they are sensitive to polymer conformation. And as normal in spectroscopy, signal width or the broadness of a line is actually indicative of the degree of order or the degree of disorder in a sample. So it's not very useful to take measures unless you have what I call interpretation models. And we use this model for cellulose. This is a model of a cellulose fibril. And it's been established over a long year, and we used lots of different techniques, and we have confirmed this picture of what a cellulose fibril isolated from wood typically looks like. And I know that this is far from this is far from established. This is still very controversial because probably you are aware of that there have been models proposed for a fibril that is an 18 chain model, a 24 chain model, a 36 chain model, and this particular depiction is a 49 chain model, I think. But I think it's important to keep things apart here, because when I try to be clear on the fact that we are dealing with isolated cellulose. And to me, there is not any obvious reason why cellulose immediately after its biosynthetical inception in a living cell should be the same as cellulose isolated with a rather aggressive chemical treatment from a dead cell. It's not obvious to me that these are necessarily the same. And with all the measurement techniques that has been available to us, we have not actually been able to find these very small structures in isolated cellulose. So this model functions. And as a model, it is just that. It is a model. It doesn't look like this, of course, but it's useful, and it's been functioning for more than 2 decades to serve as a basis for formulating hypotheses. And so far, I'm sticking with it. And as long as nobody managed to falsify it, I will continue to do so. But the fibril, I would say, is the sort of in cellulose is the most inert, it's the more inert structure. The fibril aggregate, there we can affect more. History of isolation procedure and drying and re-wetting and so on affects the lateral dimensions of fibril aggregates more. And once again, this is just a schematic, a model that shows what we mean with the fibril aggregate. And once again, it doesn't look like that, but as a model, it serves a purpose. And there's nothing wrong with simple models as long as they work. So what information can we get from NMR spectra? Well, first of all, just looking at spectra can give a lot of information. Now, I will show you an example of that later on. But I mean, eyeballing spectra is quite informative. You can get more quantitative information if you wish. We can calculate these average lateral dimensions of fibrils. I mean the average width of a fibril. We can get average width of an aggregate dimension. in a cellulose-rich sample where we know the density of cellulose, we can get specific surface area in the water-swollen state. That's not so easy to come by other methods. We can get the degree of crystallinity of the cellulose. We can utilize relaxation time measurements to track dynamics, how rapidly things move about by doing this T1 measurements. We can distinguish between different cellulose lattice types, 1, 2, 3, 4, or whatever you want to call them. This can be done normally by just naked eye, looking at the spectra. We can follow chemical modification of that occurs on fibril surfaces or of fibril surfaces. And we can also combine the specific surface area we get from NMR measurement in the water swollen state with FSP measurement and calculate average fiber wall pore sizes in the water swollen state. So it's quite useful as such and in combination with other techniques. And just to show you what it looks like, this is solid state NMR spectra recorded on some celluloses. They have all the same molecular structure, it's the same polymer, but they look the same. They don't look the same, sorry, they look very different. And the reason for that is that this technique is sensitive to how polymers are packed together. And how polymers are packed together, that is the supramolecular structure or the nanostructure, if you wish. And as it happens, a region of the spectra signals coming from the C4 atom in the anhydrous glucose unit has the best apparent resolution, so that can be taken apart and analyzed further. And that's what we do. And you get this picture shows a 2x2 fibril agate. It's just a model with different colors for some reason. But there are different states of order, different polymer domains in a fibril and a fibril agate, which you can distinguish from the spectra. And over here, to make it simple, you have essentially signals that comes from surfaces, whether they are interior to the aggregate or the envelope of the aggregate. This is what spectra looks like when you record them in water swollen state, which we normally do because it gives you the best resolution. But you can also record spectra in the dry state. You lose some resolution, but it's quite telling also to compare mass spectra from water swollen and dry materials. But nonetheless, you have surfaces here. And so if you operate your NMR spectrometer in the right way, it just counts nuclei. And that means that we have a quantitativity in spectra. We can, from the intensity of a signal fitted here, we can actually establish how many surface polymers there are. And if you take the ratio to the total intensity, I mean the total number of polymers, we can get a surface to volume ratio. And we know pretty well the width of a of a polymer. So that surface to volume ratio can be translated into a measure of the fibril width or the fibril aggregate width in nanometers, given a known cross-sectional shape, which we assume to be square in both cases. That's part of the modeling work, so to speak. So that can be obtained. And I would say that there are a few advantages with NMR if you compare with other techniques that try to achieve the same thing. And one I would say is representativity, because NMR, typically a sample we use has a solid contents of say 150 to 200 milligram. And if you look for a cellulose fibril that is about 4 nanometers wide, what's the cumulative fibril length of fibrils in that material amount? It turns out that it's about 9 round trips to the moon. So we have good representativity. And it's also a statistically stable method. I mean, we use a surface to volume ratio to take measures. And that means we have problems with large structures. As things become small, the surface to volume ratio increase, and we are getting more and more sort of precise for smaller objects. So we have a high precision. Initially, we had a debate about the accuracy, whether the measures are right. But I think that normally the sort of absolute numbers we get from NMR is pretty okay as well. But for precision, it's difficult to beat, because what we need to do in many circumstances is actually to track small changes, and then to have a method that has good precision is very good. And also, apart from many other methods, this is a method that is self-consistent. We don't have to resort to calibration curves or calibration substances to get our numbers out. We are, like all other methods, dependent on the interpretation, but that's it. So particularly for the case of determining the degree of crystallinity of cellulose, if you see measurements of degree of crystallinity in cellulose as done, for example, with IR or Raman or other techniques that are based on a calibration curve, that's basically impossible because a calibration curve requires a golden standard, and we don't have one for determining the degree of cellulose crystallinity. So that means essentially that the calibration curve is based on assumptions, and that means that it not necessarily correct, but NMR doesn't suffer from that problem. Once we have our description of the C4 region, we can get that number out, and we are independent of both calibration curves and substances. I talked about eyeballing, and I think this is a pretty good example of eyeballing spectra. We don't need to do any particular sophisticated analysis here. This is fibers that have been temp oxidized to different degrees. And if the idea is that the temp oxidation mainly affects the surfaces of fibrils, we can basically see that here. It's essentially only the surface signals that suffer as we increase the degree of charge of the fibrils. And this is a very interesting set of spectra that I could talk about at length, but I won't. But it's just an illustration to show that once we have the basic understanding of the spectral features, we can immediately understand and say that, well, yeah, we most likely have a surface modification of fibrils here. Combining FSP and solid state NMR, the measure you get if you from the FSP can be recalculated into what I would call a specific pore volume for the fiber wall. So that's the volume of liquid in the pores per unit solids. And the specific surface area from NMR is the surface area per unit solids. And that means that they are normalized the same way. They are measured under the same condition. Both are measured in the water swollen state. So you can easily combine them. And you combine them by just dividing the specific pore volume with the specific surface area. And then you take a volume and divide by an area, and then you get a length. And that length is the thickness of the water layer that you would get if you smeared all the water in the pore system over all the surface area of the pore system. And that's essentially half the average pore width or pore size. And we can get that from combining these two measurements, and we get it without needing to assume any particular pore shape. And this is very useful, and I will show an example maybe later on about that. So we can get average pore sizes as well. Okay, the example is here. So putting things together. So when making adapted pulps, the first thing we was thinking about was that we want to try to make a fiber that has a very large fiber wall pores, and it should be rich with respect to cellulose. And the thinking was done, we were then aiming at enzymatic reactivity. The thinking was that enzymatic reactivity should actually be dependent on accessibility, because if the pores in the fiber, the average pore size is much smaller than the enzymes can only chew away on the fiber surface, the envelope of the whole fiber, which is about a square meter per gram. If you can open up the pore sizes so they become much larger than the enzymes, they could enter into the fiber wall interior, and you would have all the 150 square meters per gram available or accessible to the enzymes. So that was the idea, to see if we could show that. So we identify processing conditions by the trial and error approach. We used 3 different processing steps. We had wood chip pretreatment, cooking, oxidant delignification. And we changed conditions during this until and then we sampled and then analyzed. And we took typically then measures of the average pore size. And when we made a processing condition change, well, did it result in an increased pore size or a decreased pore size, or didn't make any difference at all? And by doing that over and over again, we could come up with a target material that had a much larger average pore size than we typically had before. So I could say that the results are they are basically summarized here then. So enzyme sizes are about 5 to 10 nanometers or something like that in this particular cocktail of enzymes that we use. So you can see that if you go from the bottom here, we have a material that has about 5 to 10 nanometers. The conversion is slow initially, and we don't manage to get much conversion over a long time either. We increase the pore size slightly and it goes up, and then we do it even more and so on. And eventually this designed or tailored or adapted pulp, where we try to get the pore sizes as large as possible, we can increase both the initial reactivity and the overall reactivity significantly. And it's another interesting thing here as well, and that is that if you look at the numbers to the right here, which are the crystallinity or the degree of crystallinity, there isn't much change, or there isn't any sort of systematic change with the degree of crystallinity and the enzymatic reactivity. Now, I should say that these are materials that have fairly similar fibrous dimensions, so they don't change either. And I mean, that's what's reflected in the degree of crystallinity, really. But crystallinity as a controlling factor for enzymatic reactivity, well, it could be one, but accessibility or the access to the interior of the fiber wall by increasing the pore size is definitely a controlling factor too. Yeah, so if I should try to conclude this, I don't know of the time now, how long I've been talking, but what we did to try to deal with this was that we took and added on top of the normal analysis we do with our pulps 4 more methods, 2 chemical, 2 structural. And we had the sugar analysis, the molecular mass distribution, the fiber saturation point, and the solid state NMR spectra. And by using these 4 additional technique in this extended analysis package, it became possible to identify processing conditions for tailoring adapted pulps. And I think that's the outcome of it all, that with these 4, there might be others. And depending on what your target properties of a fiber wall is, you might have to include others. For example, we have been dealing now with cellulose, not chemically modified cellulose. I haven't used, we didn't take any charge measurement for this purpose, but that could be others as well. And of course, if you have access to more advanced structural characterization techniques such as X-ray or X-ray scattering, we can use that too. But these 4 worked for this particular purpose. And also what came out of this, I would say, is that I think it's important that we develop an understanding for how the chemistry we use during processing or isolation, or what you want to call it, how that interact with the fiber wall nanostructure is actually an rather open and unexplored field, which I think deserves attention. And talking about attention, thank you for your attention. I'm ready.
Thank you very much, Tomas. We are open for questions from the audience, and we have one question already. It's Eva Malmström who writes a question here. I will read on my other screen, so I will look that way.
Yeah.
Thank you very much for a very good and informative lecture. I'm curious about the micrographs you showed quite early in the presentation. What are the whitish dots in the right-hand side micrograph? So I don't know if you should show.
I don't know if I'm sharing now or not.
You're not sharing currently, so you can.
Okay, I'll try to share it again, and like that one, and share. In the right one. Yeah. The simple answer to this is that I'm not sure, but I think that these images are made after sputtering. And it might be from that, but if it's, or is it these structures that are indicated, or the question concerns?
We have a little delay to YouTube, so I don't know if you can get a live answer, but I hope that you answered. Yes, now we get the, yes, you answered. That was what Eva was looking for.
Yeah, I mean, it's ends. I think it's ends of strands, whether they have been ruptured by preparation or if it's some kind of artifact that comes from this sputtering. I'm not sure. I can't say really. This is actually from Isabelle Duchenne's PhD work, so maybe it's giving some explanation there.
So let's see if we have any other questions. I too thank you for a very nice presentation. And for you who will want to look at it again, we will make it available on YouTube. So if now we have a question from Lars Evenes, and I think I will make it so that you will be able to say the question. I unmute you here on Zoom. So hi.
Hi.
Okay.
Do you hear me?
Yeah.
Thank you very much, Thomas. I was thinking about the CP mass spectrum, and you mentioned and described mathematically also this, how you determine the average fibril dimensions that we've been working with, and I've been working with it too. And then I was thinking about polydisperse. I mean if you not have an average, let's say you have a dispersion of different dimensions.
Yeah.
Can you get that too in some way?
You have to, I think you can, but then you have to introduce some more assumptions. I mean, you need to assume something, because we are essentially, the measurement value is a scalar. We don't have access to a distribution. If you have possibility to do some form of partial relaxation, so you can reveal some part of the signal that is more prominent than something else, maybe you could establish that based on some form of measurement. But I would say that it's mainly about the dispersion or the distribution
Yes, sir.
of fibril aggregates. Because I had this, a couple of years ago, I had this discussion with Henri Chancey, and I asked him the following rather simple question, and that is, if you isolate fibrils from a single species, are they reasonably monodisperse? And he said yes, with one exception. The only place they haven't managed to find monodisperse fibril dimension was in tunicate cellulose.
And that means the elementary fibril, you mean then?
Yeah, somehow, but it's also funny, because if you think about the dimensions we get for fibrils, which is say 3 to 5, something like that. Normally I would say just 4. But if you take an 18 chain model, if that is what goes on during biosynthesis, well, then a 47 polymer fibril is actually composed of several 18 chain structures. And are they sort of always bundling together in a fixed number, or can there be a dispersion or a distribution of fibril widths as well? I can't really tell. I don't think we have the sort of measurement accuracy to really tell yet.
How about the other techniques you mentioned briefly? Do you know if there is anything about distribution contributions from other techniques?
No, but the funny thing is that when you take the same sample material and you look at, for example, Sachs profiles recorded on water-swollen cellulose, we have significant signal intensity in regions where you have a spatial wavelength that is much smaller than a fibril. And to me, I mean, that tells me something.
Okay.
So thank you. Yeah, and we have just two thank yous from Anastasia Rezanova and Daniel Söderberg, who both thank you for a nice presentation. And I think we all got some things to think about when choosing the analysis of our fibers. So if there are no other questions, then we thank you, Tomas, very much
Thank you.
And I just wanted to remind you that we will be back with a new fiber seminar on the 1st of December. So keep your eyes open for that. And thank you for you in the audience who participated in this seminar.
Thank you. Thank you a lot.